Welcome to Lab Module number 6, Structural Stiffness of Materials and Flexural Rigidity. In this lab module, we will explore the concept of structural stiffness of materials. You will recall in a previous lab, we've measured the elastic modulus or the material stiffness using wave speed measurements. In this lab, we're going to use a material stiffness combined with geometrical changes of a material component in order to control and tailor the overall stiffness of the component. In this case, the component will be a simple cantilever beam. The purpose is to demonstrate that stiffness in a component can be achieved through two different paths. One path is by changing the material of choice, where the materials have different elastic moduli. And the other option is to change the geometry of the material used in the component or structure so as to optimize the structural stiffness of the component. Of course, as an engineer, you have the option of combining both changes in elastic modulus and changes in the component design, to optimize the overall structural stiffness. The underlying goal of this lab is to teach you the difference between a material's intrinsic stiffness or elastic modulus and the concept of structural stiffness, which combines the material's elastic modulus with the material's moment of inertia in order to design or optimize the overall stiffness of a structure or a component. In many applications, we tailor the material's shape to contribute to the performance of the structures made from those materials. For example, we often alter the texture of surfaces in order to change, for example, touch and feel, or the coefficient of friction for anti-skid behavior, and so forth, in order to achieve a performance from a given material through changes in the topology of the surface. The surface topology, for example, can create separation between water on the surface and your shoes to reduce the chances of slipping. In other applications, for example with magnets, we change the geometry of the material in order to create separate north and south poles on a magnet to be able to best utilize the magnetic attractive force of the component. Similarly, with materials, we can change the shape to alter or minimize acoustic noise. We often will create surfaces of very soft materials with a large amount of geometry to the surface in order to create the highest absorption capability, the geometry contributing to the way in which acoustic waves reflect and can be absorbed on the surface. For materials used in computer applications, for example, we often use geometries on heat sinks in order to maximize the amount of surface area in order to achieve the most efficient or effective cooling behavior. Lastly, shown here is an example of a piece of polymer made into a contact lens, where the geometry of the component is used to control the focusing capability of the plastic. So in summary, engineers often use shape to alter performance or produce unique performance capabilities for materials. And so shape control is a critical part of engineering design and engineering with materials to achieve specific performance goals. In this lab module, we're going to study how shape affects the structural stiffness of components. We're going to use a very simple loading geometry referred to as a single cantilever beam. It's a beam that's held at one end and then extends out from the hinge point as a rod or plate. The beams that we're using in this lab comprise 4 different geometries and 2 different materials. 2 bars are going to be made out of steel and have a rectangular cross-section, one solid and one hollow. And then there'll be two aluminum tubes, one small diameter thick-walled bar and the other a large diameter thin-walled bar, both made out of aluminum. In each case, we've tried as best possible to achieve similar mass per unit lengths of each bar. In other words, the bars are designed to weigh as similar to each other as possible. The two steel bars have similar masses, and the two aluminum tubes have similar masses to each other. This similarity in mass per unit length allows further engineering assessment of the role shape can contribute to overall stiffness. As a simple demonstration of the concept of how geometry and the orientation of a beam to the loading direction affects the stiffness that the component can provide, we're going to demonstrate it with a thin metal ruler. The geometry of the cross-section of the ruler is a very thin rectangle. It's a ruler about 12 inches long, but the cross-section is approximately 1¼ inches tall by about 1/16 of an inch thick. If we hold the ruler so that the flat surface of the ruler, with the numbers scribed into it, is horizontal, we can take the ends of the ruler and bend the ruler quite easily around the axis of rotation indicated by the black dot and the circle. However, if we take the ruler and simply rotate it 90 degrees so that we're looking at the flat surface of the ruler with the inscribed numbers, and we now try to bend it in the same manner, you can see how stiff this orientation of the ruler is relative to the previous one. Keep in mind here that we haven't changed anything about the material or even the geometry of the ruler. We've simply changed the orientation of that geometry relative to the bending axis. In this case, when we have the ruler as a flat surface in bending, the height of the ruler is very small and the flexibility of the ruler is very high. It bends rather easily. However, when we rotate by 90 degrees and make the height of the ruler large relative to the other dimension, now we can achieve a very high stiffness. This is the concept that we're going to use in this lab. That geometry and the orientation of that geometry relative to the loading direction is key to optimizing overall flexural stiffness. In the case of the beams we're using, there they have the same geometry around their central axis, so that the orientation of the beam relative to bending is unchanged, but the geometry of the beams themselves vary. Shown here are schematic drawings of the 4 different geometry cantilever beams that we will be using in the lab. The 2 on the left, the rectangular shapes, one solid and one hollow, represent the type of rectangular cross-sections for the 2 steel bars being used. On the right are 2 circular cross-section tube geometries, which represent the 2 aluminum bars that we will be using. One is a thick-walled cylinder, and the other is a very thin-walled cylinder. But the mass per unit length in each of these was chosen to be very similar to each other. Sufficiently similar masses for the pairs of bars, that differences in the stiffnesses will be attributable to the geometry rather than the overall mass of the bars themselves. To begin, we need to introduce the concept of the moment of inertia, or the second moment of area about an axis, for these different geometries. the moment of inertia is given as capital I, which is the integral of the vertical axis, y, squared times dA, where dA is an infinitesimal area element of the shape. In each case here, the value of I, the moment of inertia for the different geometries, is given by the equations below each figure. In the case of the solid rectangle, the moment of inertia is quite simple. It's the base b times the vertical dimension h cubed divided by 12. In the case of the hollow rectangular cross-section, the dimensions of interest are h1, h2, and b1. The moment of inertia I is given as h cubed times h1 minus h2 divided by 2 times 1 plus 3 times the b dimension divided by the h1 dimension. In this case, h1 minus h2 divided by 2 is the thickness of the rectangular cross-section wall. For the case of the circular cross-sections, the equation is the same for both geometries shown here. The moment of inertia is equal to pi divided by 4 times rho 0 to the 4th power, where rho 0 is the radius to the outside of the cylinder, minus r sub I to the 4th power, where r sub I is the inside radius of the cylinder. This reduces to approximately pi times r cubed times t, when the t represents the thickness of the wall and when that wall thickness is rather thin. In this lab, we will investigate the influence of the material cross-sectional geometry on the deflection and maximum strain in each bend bar during cantilever loading. The deflection of a cantilever beam is defined as delta, which is equal to P, the load, times L, the length of the bar at the point where the load is being applied, cubed, L cubed, divided by 3 times E, where E is the elastic modulus, times I, the moment of inertia for the given geometry. We're going to measure the deflection of each cantilever beam under a given load with the load applied at a particular distance L for materials with modulus E and geometries having moment of inertia I. The product of elastic modulus E times the moment of inertia I is referred to as the modulus of rigidity. This is where you as an engineer have control of the design space of the choice of the material and the choice of the geometry for your beam. That allows you to maximize the overall structural stiffness, increasing either I or E or both, increasing the overall stiffness of your structure through judicious choice of the geometry and the material property of the elastic modulus. For each beam involved in this experiment, we have made 4 different loading lengths for the load to be applied to each cantilever beam. Shown here in the diagram are the lengths corresponding to L1, L2, L3, and L4, the lengths where each load is going to be applied to each beam. The objective here is that as we change the distance L, the deflection of each beam will be different based on where the load is applied. We're going to try to correlate the loading position L, where the load is being applied to the beam, and the deflection the beam is experiencing. If we go back to the equation given previously for deflection, we know the deflection is a function of the load and the loading distance. Since the deflection scales with L cubed, changing the loading distance will have a significant effect on changing the deflection. And that's part of what we're trying to test here. In addition to measuring the deflection of the beams for each loading condition, we are also going to measure the strain in the beam for each loading condition. In this case, we're going to measure the strain, which again is the change in length divided by the length of the material undergoing bending. And we're going to measure it very close to the hinge point of the cantilever beam, where the largest strain will occur. As you may recall from a previous lab, where we determined elastic modulus using wave speed measurements, I explained how difficult it is to measure strain, particularly elastic strains, where the physical displacements are very small. To measure strains in this lab, we will employ the use of a strain gauge, a small electrical resistor, typically in the form of a copper wire on a substrate, and the copper wire has a very long length in a very small area. It's shown in the diagram to the left. The copper wire acts as a resistor, and as the strain gauge is stretched or compressed, the resistance of the copper wire will change, and that changing resistance will be used to evaluate the amount of strain, whether stretching or compressing, that the material is experiencing. We've built a special fixture for assessing the strain directly, and each cantilever beam to be used in this lab has a strain gauge mounted on it, right at the hinge point on the top surface of each beam. We will be using that strain gauge in order to measure the strain introduced from the loading of the beam. However, the change in resistance of that gauge itself, even when strained quite a lot, is a very small value. And that small change in resistance is often very difficult to measure. So as a way to increase the resolution of that measurement, we employ the use of a Wheatstone Bridge, a special circuit developed in order to evaluate the change in resistance of a strain gauge. I will explain how a Wheatstone Bridge functions next. So a second objective of this lab is to teach you how strain gauges work and how strain is measured using strain gauges based on the application of a Wheatstone Bridge. The schematic diagram here shows you the layout of a typical Wheatstone Bridge. A Wheatstone Bridge is a very simple electrical circuit where there are 4 resistors connected around effectively the perimeter of a square. Resistance R1 is connected between pins A and B. The resistor R2 is connected between pins A and D. Resistor R3, is connected between pins C and D, and the 4th resistor R4 is connected between pins B and C. This circuit requires at the start that the resistors R1 through R4 are identical in value. One of those resistors is then replaced with a strain gauge itself having the same resistance as the other 3 resistors in the circuit. Now if you consider inputting a voltage across pins A and C, current wants to flow along the path ABC as well as across the path ADC. So if one of the resistors, say R1, is connected to a strain gauge, and that strain gauge is then stressed or compressed so that the resistance changes, then the current will have a more difficult time flowing along the path ABC, and so more current will flow along the path ADC. Since there are differences in the current flowing across those two paths, a voltage is generated between points B and D. In this case, that difference in the ability of current to flow along the two paths allows an output voltage to exist between points B and D, and the magnitude of that output voltage depends on the variation in the resistance of R1, which is the strain gauge. As the resistance R1 changes, the scale of the output voltage will change. The output voltage is also a function of the input voltage, and it's a function of the difference in the resistivity of path ABC versus the path ADC. And this is how we employ a Wheatstone bridge to make measurements of strain. As you look at the circuit here, resistors R1 and R4 are in series, and resistors R2 and R3 are also in series. Similarly, if you look at resistors R1 and R2, these resistors are in parallel, and resistors R3 and R4 are also in parallel. This is the typical setup of a Wheatstone bridge. When all four resistors are exactly balanced with each other, meaning they have identical resistances, then there's no difference in the current that flows between A, B, and C versus A, D, and C. Therefore, if we try to measure a voltage across B and D terminals, that voltage would be 0. That's defined as a balanced Wheatstone bridge. This is the starting condition for using a Wheatstone bridge. However, as any of the resistors change in value, for example, replacing R1 with a strain gauge and then straining that strain gauge to change its resistance, then the path ABC becomes different in terms of resistance, higher than path ADC, and that produces a voltage output across pins B and D. That output across B and D makes the circuit unbalanced and leads to a voltage being created across pins B and D. The Wheatstone bridge circuits lend themselves to the ability to measure small resistance changes and can be configured to utilize multiple strain gauges. In the first configuration we just showed, the circuit is referred to as a quarter bridge because one of the four sides, one side of 4, 1/4 of the sides involves a strain gauge being placed into the circuit. In this case, the resistance of the strain gauge starts out identical to the resistance of the 3 other gauges of the Wheatstone bridge. However, we can also change or add a resistor to the other side of the circuit. In the second case, we've replaced 2 legs of the circuit with strain gauges. So half of the circuit involves strain gauges, and this setup is referred to as a half-bridge strain gauge circuit. The last Wheatstone bridge configuration on the right is where all 4 legs of the circuit involve strain gauges. And this is what's referred to as a full bridge strain gauge circuit. In these cases, utilizing more than one strain gauge can be a way to amplify very small deflections or very small strains. To review again, here's a simple Wheatstone Bridge configuration. The four sides of the bridge can each contain a resistor, and those resistors can either be fixed resistors, variable resistors, or the strain gauges intended to be used. In the initial condition of the Wheatstone Bridge, all four resistance paths have to have an identical resistance. So to begin, R1, R2, R3, and R4 are all set to and are identical resistances. The power source, or the input, is put across pins A and C. So if you think of this power source as a battery, for example, a battery has a plus and minus terminal. And if we put the minus terminal at point A, pin A, and the positive terminal connect to point C or pin C, then electrons from the battery want to flow from pin A across the legs of the circuit towards pin C. The negative end of the battery is pushing electrons out, and they're being drawn to the positive side of the battery at point C. If they have two choices to flow towards point C, the electrons can flow along path ABC, or the electrons can flow along path ADC. If the resistance of the two paths are identical, then there's no difference in the current flowing across the two paths, and therefore I measure no voltage across pins B and D. I will see no voltage output. However, if the resistance of either path changes, then there will be an output voltage that's measurable across pins B and D. Here we show you our Wheatstone Bridge, which I refer to as a plug-and-play Wheatstone Bridge. It's been built specifically to show all the details of how the circuit is configured and allows the flexibility for any of the four sides of the circuit to be changed between a variable potentiometer, where we can adjust the resistance of each leg, or have an input of a strain gauge along the leg. So let me outline the layout of this circuit. If we look across the top edge, there's a red pin connection at the left side labeled A, and another red pin at the right upper side labeled B. These are the contacts across the edge of the circuit. Across the connection between pins A and B is a large potentiometer in the position just to the left of the contact pin B. This is a variable potentiometer, which means we can adjust it to achieve a specific resistance for that potentiometer. That allows us to have a resistance that we can choose and can tune to match the other resistors in the circuit. To the left of the large potentiometer, directly below the label R1, is a switch. It's a three-way switch, and it's currently in the position to the right. In this position, it indicates that we're selecting the potentiometer to be in the circuit path between A and B. That switch can be switched to the middle, in which it creates a break in the circuit, or it can be switched all the way to the left, and when it's switched all the way to the left, it brings into the circuit the connectors, black and red pin connectors, located just to the left of the switch itself and just below the switch. We can then input a connector between the black and red connectors, such as a strain gauge. And when the switch is switched all the way to the left, the strain gauge itself becomes the resistor R1 in the path between pins A and B. If you follow this logic around the perimeter of the Wheatstone Bridge, you will see that each side of the Wheatstone Bridge plug-and-play platform has the same setup. It involves a pin at each corner. So for example, if you look at the right side of the board, the red pin at the top right, labeled B, and the white pin at the lower right, labeled C. And then between those points, we have again the potentiometer, a switch next to the label R4, and then just above the switch, there's another black and red connectors that allow us to put a strain gauge into the circuit. When the switch is switched to the down position here, it puts the potentiometer, the variable resistor, into the circuit. When it's switched to the middle position, there's a short between pins B and C, and when it's switched all the way up, it puts the connector pins red and black, which would have, for example, a strain gauge plugged into it, puts that strain gauge then into the resistance path. And that approach continues along the bottom and again along the left side of the resistance paths R3 and R2. There are two more connectors on this plug-and-play board. There's an input, which is a large red connector with a red and black pin insert connector in it. We use that to input a voltage between pins A and pin C. That's the input voltage to the circuit. Pin A is connected to the negative side of the power source, or input voltage, and pin C is connected to the positive side of the input voltage. And so current wants to flow from pin A to pin C along the two outer perimeters of the circuit. If all four resistors R1, R2, R3, and R4 are all identical, then the path along ABC and the path along ADC have identical resistances, and therefore there's no difference in the current that will flow along each path. And therefore, if we measure the voltage between pins B and D, we will have zero voltage. To facilitate measuring the output voltage between pin B and D, again we've installed a connector in red labeled output, where the voltage between B and D can be measured at this connector. We will later put a connection in here to measure the output voltage using a multimeter. Before beginning to utilize strain gauges, we need to set up the Wheatstone Bridge to match the resistance of the strain gauges themselves. Throughout this lab module, we will be using strain gauges with an initial resistance of 350 ohms. Therefore, before using the Wheatstone Bridge, we need to establish that all four sides of the Wheatstone Bridge have a resistance of 350 ohms. In other words, we need to make the Wheatstone Bridge balanced. Since the resistance of the strain gauge is very accurately 350 ohms, we need to set the potentiometers on each leg of the bridge to 350 ohms. We do that by putting in a connection across each side of the Wheatstone Bridge. For example, we measure the resistance between pins A and B and then switch to have the potentiometer, or the variable resistor, along that side of the bridge in that circuit and adjust the resistance to exactly match 350 ohms. We repeat this process for each of the other three legs or three sides of the Wheatstone Bridge. Once we've set each potentiometer to exactly 350 ohms, then we can switch any side of the bridge to use either the resistor or switch it to a strain gauge plugged into the strain gauge input pins on that side of the bridge. And then we can select the strain gauge as the input simply by flipping the switch to that input side. We will demonstrate here how to tune the circuit to have all the sides be 350 ohms. And then we will show that the output of the circuit has 0 volts or very close to 0 volts when we start, prior to straining the strain gauge itself, which will be input into the circuit in place of one of these potentiometers. Once we've set up the Wheatstone Bridge, we can now demonstrate how the input of a strain gauge on one side of the Wheatstone Bridge can produce an output voltage. In the first configuration, we will use the bridge as a quarter Wheatstone Bridge, a quarter bridge configuration, which means one of the 4 sides, or 1/4 of the circuit, will have a strain gauge as the input rather than the potentiometer or a fixed resistor if we chose. Here we show an example of a long cantilever beam, in this case oriented to make it quite flexible, and we have strain gauges mounted close to the hinge point of the beam. The beam has 3 different strain gauges mounted on it. The first strain gauge we will be using is oriented so that its long axis, its most easily deformable direction of the strain gauge, is aligned along the length of the beam. This configuration allows us, when we push down on the end of the beam, deflecting it downward, it puts the top surface of the beam into tension, and the maximum tension will occur back at the hinge point on the top surface where the strain gauge is mounted. This is the same configuration that we will be using for each of the 4 different cantilever beams in the experiment itself. Here we demonstrate the input from one longitudinal strain gauge aligned along the length of this beam and show how bending the beam produces an output voltage from the circuit. Each time we deflect the beam, the output, read in volts here, goes up. And each time we unload the beam, it returns to near 0. In the second configuration, we will take 2 strain gauges and input them into the circuit. In the first case, we're going to use the same strain gauge on the top surface of the beam that goes into tension. And we're also going to pick a second strain gauge that's mounted on the bottom side of the same beam, directly below the first strain gauge on the top, and oriented in the same direction. As this strain gauge will go into compression equal to the tension on the top side, it effectively works as an amplifier. It increases the resistance change in the circuit, and therefore when we try to deflect the beam again and look at the output of the circuit across pins B and D, the output will be amplified by adding that second strain gauge. We get a much larger output voltage for the same general deflection. In the third configuration of the Wheatstone Bridge, we're going to use the top surface longitudinal gauge, the first gauge we used, and we're going to combine it now with the transverse gauge. It's the same strain gauge as the first one, but it's now rotated 90 degrees relative to the surface of the bar. It's also located on the top surface, back at the hinge point. However, since we're bending the bar by pressing down at the end so that it bends in its most flexible condition, the transverse strain gauge, which is measuring strain across the width of the bar, will have no strain occur. So that strain gauge doesn't see a change in resistance, even though we have two strain gauges input into the circuit. The one longitudinal one on the top is seeing all the resistance change, whereas the transverse gauge sees no resistance change at all. We can utilize in actual structures combinations of strain gauges oriented in many different directions relative to the deflections the structure experiences in order to actually determine what kinds of strains are occurring in each direction in the structure. Now let's move on to measuring the deflections of our single cantilever beams used in this experiment. The first beam, number 1, is the solid cross-section steel beam. To measure its deflection under load, we have a small deflection gauge that can be set up against the surface of the beam exactly at the point where we're going to apply the load. This is a very simple displacement gauge that can be read directly on its face, the displacement of the gauge relative to the beam for each loading configuration. Okay, so the way we set this up is we're going to align the deflection gauge so that the moving pin, which moves up and down inside the gauge as the position of the gauge changes relative to the beam. Then, as the beam is loaded and the beam deflects, the pin moves out to measure the changing position of the beam. In order to get accurate measurements of the deflections, what we're going to do is set up a basket to hang from the beam at each of the 4 length positions L1 through L4. For each case, we're going to load the beam with 1 kilogram of load. So before applying the load, we need to attach the basket and then zero the displacement of the beam under that condition of just the weight of the basket being applied. We also zero the strain gauge output at the same time. Now we will apply the weight to the basket, and that weight will load the beam and make the beam deflect. And we will measure the deflection distance. Using this deflection gauge for each experiment, we're going to measure the deflection with 1 kilogram of load at each of the 4 positions along the beam length and for each of the 4 beams. We will make a total of 16 different deflection measurements using the 1 kilogram load. And in addition to each deflection measurement, we're going to measure the strain from the strain gauge mounted on the back end of the beam at the hinge point. In addition, for each load condition, meaning 1 kilogram at each of the 4 load positions on each bar, We're going to also measure the strain of that longitudinally oriented strain gauge mounted on the top surface of the beam located at the hinge point where the beam attaches to the frame. So each measurement consists of a load, 1 kilogram, at a length L, with a displacement being measured by the displacement gauge and a strain being measured by a strain gauge. And then we're going to see if the data is consistent with a material of a certain modulus. And that modulus is known for steel and aluminum, the two types of materials being used. We're going to do that for the different geometries at the different loading lengths, and the different geometries bring in different moments of inertia. And we'll see how that moment of inertia affects the deflection behavior of each beam. So in total, there will be 16 measurements, 4 measurements of each beam, 4 different beams consisting of 4 different geometries and 2 different materials. 1 material being steel for the rectangular cross sections, and the other material being aluminum for the 2 circular cross-section beams. To reduce the time of this video, we will demonstrate just a few of the loading configurations, but the same procedure is used to make all 16 measurements, and the data from those measurements are summarized at the end of the video. During this lab exercise, we will be measuring the 4 different loading positions for the first beam, and then we will do the measurements for the first loading position for each of the other 3. It's worth noting that for the actual experiments, we are not using the Wheatstone plug-and-play platform. That was a demonstration module. In the actual experiment, a Wheatstone bridge is built into the white box on the right side of the loading frame, where the black knob selects between beams 1, 2, 3, and 4, and the display is set up to read the output of the Wheatstone bridge between pins B and D. But the entire Wheatstone bridge and its power supply are all contained inside the white box mounted on the right side of the load frame. Here we show a summary table of all the data from this experiment. The load 1 kilogram is shown, the bar designations 1 through 4, and the lengths of the loading positions L1 through L4 for each bar. And then there are measured deflections from the deflection gauge for each position, and the corresponding strain for each condition as well. Strain has units of microstrain. So the first value in the table, which is shown as 0.154, would indicate 154 microstrain. The next value would be considered 117 microstrain, and so forth down the table. From the data collected, please provide this table showing the bar identification, the 4 distances along the bar for each bar, the weight applied to the bar, the bending moment applied to the bar, meaning the force at a length. The bending moment is the force being applied at a length of the bending bar. Also, the measured deflection at each loading distance and the measured strain at each loading distance. Then add 2 columns to the table. One column should be the elastic modulus value derived from the measurements for each beam and loading position. And the last column should be the modulus of rigidity calculated for each bar. For each bar, and using a weight again of 1 kilogram, plot the deflection versus strain to see how well they correlate. In addition, calculate the stiffness, the load P divided by the deflection delta, as a function of length. In other words, the loading position lengths, so that you can plot basically the load divided by deflection on the y-axis versus the length of the loading arm along the x-axis. Further, plot the product of P, the load, times L cubed, and plot that value versus the deflection. What then does the slope of that data represent? From this slope, calculate the elastic modulus of the steel and aluminum bars and compare them to their known values or literature values. Calculate the product of the elastic modulus and the moment of inertia, the product EI, or modulus of rigidity. Explain which bar has the highest value and what drives that value, and which bar has the lowest value and why. How do the values of the modulus of rigidity compare to your observations of deflection? Recall, the higher the modulus of rigidity, the stiffer the bar should be. The cross-section dimensions for each of the cantilever beams are provided in the lab manual PDF file on page 7. The end. Good luck.